Thank you. So my purpose today is to teach you a little bit about photoemission electron sources for accelerators. This talk is targeted for people who feel like they need or want to learn something about it, particularly non-physicists or people who don't know what photoemission is really used for in physics. So I'm sorry for you who are experts in this. I will be glossing over your glorious subfields with impunity. And so sorry at the beginning, but throughout the whole time, you can read my whole outline, but the most important thing I wanted to mention is that you should feel free to interrupt me if you're not getting something, particularly students. Students have carte blanche to just yell at me and say, I don't get that. Everyone else should raise their hand, though. Okay, the first thing I want to talk about is brightness. I'm the first pedagogical talk, and so what is beam brightness and why do we care about it? Brightness characterizes a beam's phase space density. Phase space is the six-dimensional space of 3 coordinates and 3 momenta. And whenever I write down a blob, which is corresponding to the density, I'm talking about the density for n electrons, where n is the number of electrons in a bunch, and it depends wildly from 1 to 10 to the 10, depending on the application. The brightness, if we want to start with the concept of brightness, we simply ask about the 6-dimensional density at a given position and a given momentum. This is a 6-dimensional object, but in practice we project down to the planes xpx, ypy, zpz. When we do that, we have another blob in this space, and we want to assign an area, because at the end of the day I want to get a number for brightness, not a 6-dimensional object. We assign an area in the RMS sense, where I take the RMS length here, the RMS length here, and I subtract off of any correlation, and I call that area the emittance. This is an important term to remember. The emittance comes up over and over again. To create a brightness in 6 dimensions, I take the emittance in the x-plane, the emittance in the y-plane, the emittance in the z-plane, and I use that as a 3-dimensional, as a 6-dimensional volume. I simply divide the number of particles in the bunch by the 6-dimensional volume, and that, up to some scale factor, is the definition of brightness used in many applications. Sometimes you'll see a slightly different version of the brightness in which instead of using the momentum in this epsilon z, we omit the momentum and use n over t or n over z, where z is the direction of motion, always in this talk, as the peak or average current. And we call that the 5D brightness. That's a finer point. Don't worry if you didn't catch it. Okay, a huge swath of accelerator physics, machines large and small, are dedicated to maximizing this parameter. The machines, some examples, for instance, colliders and other HEP machines which have length scale of many kilometers. The luminosity or the efficiency of data collection is proportional to the brightness. Free electron lasers, a revolution in photon sciences, providing a huge X-ray power for materials in biological studies, have a gain length that's inversely proportional to brightness to the 1/3 and an efficiency proportional to brightness to the 1/3. So the brighter your beam is, the less expensive your free electron laser is. These are also kilometer scale devices. Storage rings also are radiation-producing devices that do very similar work as X-ray free electron lasers. The electron beam brightness is the concept that constrains the radiation's brightness, so we care about it deeply there. In electron microscopy, now going down to the tabletop scale, electron microscopy and diffraction, the concept of the flux that is coherent inside of the beam is linearly proportional to the brightness too. Okay. So let's talk about the difference between the 2 accelerator archetypes you saw there. You saw a ring and you saw a linac. In a ring, there are billions of revolutions. The max brightness of a ring is very different than, say, a photocathode source, which I'll be talking about. The max brightness is set by an equilibrium balance among a lot of different effects. The beam is talking to itself, the beam is radiating away momentum, and it's interacting with the guide electromagnetic fields. This is all in theme 3, and I don't have time to talk about it now. A linac source is very different. The beam is born, it's accelerated, it's used, and then it dies. Examples of linacs are electron microscopes, linac colliders, energy recovery linacs, free electron lasers for the most part. To a good approximation, the phase space density undergoes incompressible flow, or Liouvillean flow. And if this is the case, then the maximum brightness we could ever have, the maximum phase space density, is the maximum phase space density at the source at the time of the beam's creation. This is why, for linear accelerators, this is why the source is so important. So imagine we have a source. I'm not saying it's a photoemission source. I'm saying it's any generalized source. It has some size, sigma x, and it has some intrinsic momentum spread, sigma p. If it goes through a transport system and the forces are all linear in position, they're all perfect lenses, the phase space density and area is preserved. The phase space is simply sheared and rotated, but the final emittance is equal to the initial emittance. And the initial emittance is just the product of the initial size times the initial momentum. Now, in an arbitrary transport system, you might be able to see that here. I don't know if it's bright enough, but I've included some nonlinearity in the electromagnetic fields. And so the phase space gets a little bit of a twist. Now, when I draw the emittance box, the emittance grows because the RMS dimensions have gotten larger. However, there's an important thing. The source still matters, because if we looked at the phase space density right here at the center, the phase space density there, since we're undergoing incompressible flow, is constant, still set by the initial source parameters. So in many applications, you can cut off this part of the beam, and the beam you're left with is still determined, the maximum phase space density is still determined by the source. So the source it's very powerful when defining the parameters of a linac. So photoemission sources, photocathodes is the word I'll use. I want to remind you of this picture. So we have a source size and some source spread and momentum. And now let's think about photoemission. What determines the initial source size? And in short answer, the answer is the source or cathode accelerating field, the field on the emitter itself. So here's the emitter. I've applied some accelerating force. And say I send in some photons, each with energy h nu. Nu is the frequency of the light. And what happens is I'll emit a chunk of charge density, negative charge because it's electrons. And if I tried to emit any more, that electron that would pop out would feel the two forces. It would feel the accelerating force, but it would also feel the force of these electrons pushing back on it. And it turns out from electromagnetism that there's an image charge induced on the other side of this plate, which serves to double this effect. And so there is a limit to the amount of charge that you can possibly extract. When the repulsive force, these red lines, of the charge density exceed the accelerating force, emission turns off. There's no more accelerating field, no electrons escape. So the maximum spatial current, or the maximum spatial charge density, is at least linearly proportional to the electric field. And if just doing the proportionality, you find that this means that the maximum brightness of the sample is linearly proportional to the electric field. We heard a talk earlier today from Eileen about why the electric field is so important. This is just reiterating that point. So for the source, the electric field determines the spatial size of the bunch. What determines the momentum spread? Well, the momentum spread is actually the intrinsic momentum spread of the photoemission. Ivan mentioned this earlier. So let's imagine a case where I have a very high emittance material, and I'm accelerating in this direction now. I send in some photons. What does high emittance look like? It looks like a very disordered momentum space, that the particles that are emitted have a large uncorrelated variance in the magnitude and direction of the momentum. A low emittance material is one which you might expect has very low transverse momentum. We can characterize the momentum spread by a few words, and I'm going to use them interchangeably. And it's good to think about them so that they're interchangeable in your mind. I think about it in my mind as an effective electron temperature. This is not the temperature of the electrons in the material, nor is it the temperature of the phonons in the material. This is the temperature of the electrons once they're in vacuum. I'll call it KTE. In the field, this is typically also referred to as the mean transverse energy. So use those terms interchangeably in your mind, because we will too. All right.
How would this be different than the temperature in the electrons in the material?
Very good question. Let's find out. A cartoon of the electrons in a material. Okay, this is a really simple picture of electrons in a material. I imagine that the positive nuclei in the material are applying some potential energy well that I can sink electrons in. So I've got a solid here and a vacuum here, and it's very common to draw these diagrams with energy on the vertical axis and position on the horizontal axis. So this there's some maximum energy when we fill the potential well up with electrons. That's the Fermi energy. And the picture I'm drawing you here is temperature equal to 0. Immediately when we fill up the electrons, we see that there's an energy scale for the electrons to be able to hop out into the vacuum. We call that, that energy value the work function. I'll call it phi here as the standard notation. Now, at t greater than 0, the top of the distribution is actually a little blurry. This is the Fermi-Dirac distribution. And the width of this blur is on the order of the, material temperature, kT. This is not kTe. This is actually kT of the material. Now, there's an easy way to get electrons out. You simply turn the temperature up, and some will escape. This was done by Richardson and Dushman, figured out between 1901 and 1930. It's called Thermionic Emission. We heard a little bit about it earlier today. This is not photoemission, but it has some interesting things that we should consider. So the spread of the momentum in this case, the spread of energies is so large that some are actually larger than, some have energy larger than the vacuum energy and can escape. Not all of them escape. They can't just have enough energy. They also have to have enough momentum in the right direction to get out. So some of them are, reflected back. Now, if we were to look at the material, if we were to look at the electron temperature, the MTE, as they're emitted, we would find out that this spread in energies corresponds to a random momentum spread equal to the material temperature. This is called the thermionic immittance. This is a very robust emission process. It's used for generating beams for many storage rings, for example. The system is in thermal equilibrium, however. We can't turn this process on and off very easily with the temperature. In order to create bunches, short bunches, needed for RF accelerators, we have to modulate the accelerating field. This poses practical limitations. The fastest we can switch these fields in typical accelerator technology is on the order of nanoseconds. However, for a lot of the applications, we'd like to push down to picoseconds or below. So this is not a good option for many of the applications that we have. I'm not going to talk about field emission too much, but if you could turn up the electric field, and you would also get a lot of electrons out because we'll modulate the barrier. This suffers the same problem that we had before. The field can't be switched as rapidly as we would need it to be. Photoemission, on the other hand, is as short as the laser pulse, which can indeed be down to the tens of femtoseconds if we so chose. This was originally proposed by Einstein in 1905, very famous. It's what he won his Nobel Prize for. We're using photons to literally knock out electrons. So what happens is we send some laser energy of energy h nu, and there's some finite reflectivity, so we bounce a little light off the surface. So we lose a little bit of light already. Okay, that's a price we have to pay. Some of it is absorbed, and it goes in to absorb a series of electrons that goes down from the Fermi level about the energy h nu. They get excited up 1 h nu. And I've drawn a subset of these electrons excited by that amount. So you can see there's some that are larger than the vacuum energy. Some escape if they're heading in the right direction, and some are reflected back. This is not in thermal equilibrium, so we have to think about these particles interacting with the rest of the subsystems. So these particles are actually capable of scattering with others and scattering back down to their original or alternative states. And so we have some losses here when we go to compute the efficiency of this process. All right, so let's talk about what the MTE would be here. What is the emitted electron temperature? Often in accelerators, we make the assumption, this is a drastic assumption, that some scattering occurs at the surface, and that randomizes the momentum. Okay, that's a very deep assumption which we'll talk about more tomorrow. However, if this is empirically true for many cathodes, particularly disordered cathodes, which are polycrystalline or other forms of disorder on the surface, but it's not true for all cathodes. If it is true, we can argue what the MTE is, or the KTE, immediately. We take the difference of the laser energy minus the work function, and we have 3 spatial directions. And due to equipartition, we divide it by 3, and that's what we get. This is the case when the photon energy is much larger than the work function. Now, you notice that if we reduced h nu such that it was on the order or less than phi, we would be sampling from the thermionic tail, and we would have an emittance that's equivalent to the emittance in thermionic emission, but now KT here is much smaller, typically room temperature. This answers your question before, that only in the case where we are at h nu much greater than phi do we have something different than the material temperature.
Only if they're scattering.
We're assuming that the initial electrons are promoted from a thermal distribution.
Yeah.
And so if they're promoted from a thermal distribution, they will have that property upon emission.
They'll have the same transverse momentum. Only if they scatter.
Oh, yes, only if this scattering occurs. Yes,
Sure, okay.
only if this scattering occurs. It's a very good, very big caveat, very important. But this has been the operating theory for many, many years in accelerator physics. So, if emission is sufficiently prompt, the three-dimensional shape of the laser maps onto the initial bunch shape. This is very good, because if we're emitting a very dense bunch, collective forces in the bunch can, during beam storage and transport, can dilute it. So we have a lot of freedom with photoemission accelerators to affect how these collective effects play out later on. So we like that a lot. But again, not really my thing to talk about. Now, we've already seen what the root is to high brightness from this picture of photoemission. The high brightness, low emittance limit is when we set the work function, set the wavelength such that we're at or less than the work function. And so this has been explored recently in a number of labs, one at Cornell and at Lawrence Berkeley, National Lab in semiconductors and in a metal photocathode. Here they're plotting emittance, here they're plotting MTE. There's a square root difference between them, but they all have the same behavior. For larger photon energies, the emittance is larger, the MTE is larger, and they all plateau towards the material temperature. They all plateau towards the material temperature. So the anticipated brightness going from the standard 250 millielectron volt operation of typical photoinjector MTEs down to room temperature, which is about 25 millielectron MTEs, is a factor of 10. This is great. Why doesn't everyone do this? Why is everyone not choosing their laser wavelength such that it's exactly at the photoemission threshold? Well, there is a reason for this. As we approach the threshold, the quantum efficiency, or the number of electrons per incident photon that we're getting out of the crystal, drops dramatically because we're not promoting as many electrons above the vacuum energy. So we're only getting emission from the thermal tail. Now, this is an issue for power-hungry applications. For instance, when applications that require a large number of electrons per second down the pipe, like energy recovery LINACs or continuous duty free electron lasers, they're often starving for laser power. So the decrease they could experience in the quantum efficiency could be multiple orders of magnitude or more. Here are examples measured on a metal photocathode going towards typical operation down a few powers of 10 near the wave function threshold. And a paper from a while ago we did where using 3 wavelengths, one very near the threshold, again a factor of about more than a factor of 10. So it's a price that you can pay, but you have to be willing to pay it. So how do we get lower KTE? We have to cool the photoemitter. Again, this is going to hurt the efficiency, but we can get at least another order of magnitude in KTE, going from 300 down to, say, 30 kelvins. So a good example of this we're exploring at Cornell for a low charge application. Hedy Lee has developed a 40 Kelvin 200 kilovolt DC gun. Now the limit here is still the material temperature. We still are going to be limited by the 40 Kelvin. Is there a way to get even lower? And the answer is yes, but we have to throw out the previous scattering assumption. We have to get with the rest of the photoemission community and find or create systems that actually conserve momentum across the barrier. So we have to ask the question, what does momentum look like? What does momentum in the crystal look like? I'm going to give a very brief, simplistic picture. I'm borrowing this slide, stealing this slide from Andreas Schroeder, who has a really nice picture of what's going on. We mentioned earlier that the electron doesn't necessarily have to behave as if it has the free electron mass inside a crystal. It can behave as if it has a heavier mass or a lighter mass. Let's look at the case where it has a mass equal to the free electron mass. So in this case, we have some distribution of electrons as a function of their transverse momentum. In this case, a very simple crystal is a quadratic relationship, p squared over 2m, not a very surprising thing. So let's say we take a group of these, delta E, and we promote them by h bar omega above the vacuum level. Okay? So some of these electrons can't get out. They are grayed out. They can't get out because they don't have enough momentum in the forward direction to actually escape. Some of them, which have small transverse momentum, actually do. and those are the ones colored in red. Now, let's look at the same case, same parameters, except we change the effective mass. We make the effective mass smaller. When we do that, the parabola, p squared over 2m star, where m star is the effective mass, is much narrower. For a given delta E range, we don't have as much momentum range. And remember, momentum spread is the thing that we're interested in limiting. So if we promote this by the same h bar omega, you can see that we're already limited by the original states of the electrons into a smaller momentum region. If you stare at this picture long enough, you can find out that you can reason out that small effective masses for the same excess energy, h nu minus phi, yield lower MTE results. This also tells you that for a given energy spread, kT, it corresponds to smaller momentum spread. Thus, the emitted electron temperature may very well be below the material temperature even in the case that the system is in thermal equilibrium. This is how we beat the material temperature limit, is we exploit the low effective mass of materials. But we have to find classes of materials that do this. So, figures of merit, I'm kind of running out of time, so I'm going to kind of go through this a little quickly. I just want to go over some of the things that we've talked about. We've talked about quantum efficiency. How do you get high quantum efficiency? You have high optical absorption, you have low scattering losses, and you have productive excitations. The excitations you produce are where you want them. Who cares about this? Power-hungry applications, laser power-hungry applications, like ERLs and continuous duty free electron lasers. Examples of these would be multi-alkali cathodes, gallium arsenide, cesium telluride. Semiconductor cathodes in general often have very good quantum efficiency of order of 1%, so roughly 100 photons per exiting electron. So we also, in some cases, want a cathode that responds very quickly, that for a delta function for a delta function laser pulse in time, we want a very short electron bunch coming out. So in order for this to happen, we need a small absorption length, and we need, for sort of complex reasons, I'll gloss over this, we also need low scattering. Who cares about this? Ultra-fast applications, where you're trying to push temporal scales of the beam down to picosecond or smaller. You need comparable response times from your cathode. And it's also very useful in a number of free electron laser designs as well. Examples of really fast photoemitters are metals. Metals emit on the order of 10 femtoseconds for a lot of wavelengths. And multi-alkalis as well, we believe they have a response time of around a tenth of a picosecond. So we want these things to be easy to use. We want the ruggedness, and we want them to be rugged and have a long lifetime. So particularly, it's nice to use non-volatile or non-reactive constituents, and we like photoemission that's relying on bulk stuff, not stuff that relies on effects at the surface. So the people who care about this, I'm almost done, I promise. I'm almost done, I promise. People who care about this are essentially everyone. You need it to be easy to use. And low MTE, we talked about what makes low MTE. And who cares? I hope all of you care, because that's the real goal of getting higher brightness from photocathodes. I don't have time to talk about this, but takeaways, photoemission was 1905. We still have a long way to go to get to ultimate beam brightness. Electron temperatures are dropping, which is great, but we still have a lot of interesting questions. See Siddharth's talk tomorrow for a discussion of how we can actually get the momentum conservation that we need. We can talk about later on what the role of multi-photon processes is, and what are the ultimate limits to MTE? Surface roughness, chemical roughness? I leave these as exercises to the reader, so go ahead and find out. Thanks.
Okay, so hopefully we can gather a few questions. Students first?
Oh, Smith first.
So when you start emission sources
Uh-huh.
and you're hitting them here with a laser,
Yeah.
how deep from within the photocathode do the electrons come from? I know it's coming from the surface, but how deep into do you get them from? When you're probing like nanometer down, micron down?
It's the penetration depth of the light, which you could think about as the optical skin depth. The skin depth for metals is on the order of 12 nanometers or so, and for some semiconductors, it can be as long as a micron. And in order for fast response, you need that actually to be kind of small because the electrons won't take so long to get out. So that's why some longer absorption length materials have a slow response time.
There's one more point here. The absorption depth of light is one thing, and the other thing is also the emission depth of the electron. So it is possible that the light actually absorbs quite deep within the material, but the electrons that are excited deep within the material don't make it to the surface. In that case, the emission region is dominated by the escape depth of the electron.
That's right.
Which can be a few nanometers per metals.
Yeah, for instance, if you're deep in the crystal and you scatter before you get out,
Right.
that
Do you get any emission flow from electrons scattering as they come out?
you can. There are some scattering events which can preserve the life of the electron as it's excited. Some won't.